Okay, great. So today is January 19th, 2021. Tuesday after a 3-day weekend. Hopefully we all feel a little more rejuvenated than we might otherwise feel on the first day of a week. It's only a 4-day week, so it'll feel a little quick as well. We are going to, just to put it on your calendar, we are going to have an exam on Thursday. Okay, so we're going to have our first unit exam Thursday. This is a big deal for you all. It'll be a lot of points. It will, of course, be 100 formal points. And so I want you all to be aware of that, to start to study. We are going to take a review day tomorrow. Today is really the last day that we're introducing new material. So I want you all to be prepared and begin to study. But today's lesson is going to address those same objectives that we introduced on Friday when we talked about enzymes, but we're going to add on. So we've got this essential question that we really want to be able to answer by the end of today's lesson, which is, what does it mean for enzymes to have an optimal environment? That's directly tied into the second of our two objectives, which states that biologists will be able to explain how an environment can impact an enzyme's ability to function. All right. So in review, we talked about this on Friday, but in review, enzymes are three things that we want to focus on. Number one, enzymes are catalysts, which means that they speed reactions up. We introduced that vocabulary word on Friday. A catalyst is something that speeds things up. It speeds a process up. So in the case of enzymes, they speed up reactions. Number two, enzymes are specific. So enzymes work only with unique substrates. They can work only with substrates that have a specific shape. That shape has to be compatible to the enzyme's active site. And number three, an enzyme is reusable because it goes unchanged in the course of a reaction. All right, so those three qualities are extremely important, and they are what make enzymes such special compounds for biological organisms. Almost all biological organisms make use of at least one class of enzymes that helps them to produce energy, or that helps them to digest foods or to synthesize new products. But enzymes are absolutely essential to life. Can someone remind me which of our four biological macromolecules is an enzyme? I believe this came up in the warm-up. But which of the four macromolecules is an enzyme? Is it a protein, a carb, a lipid, or a nucleic acid?
Protein?
Yes, good, Kathy, thank you. And so because enzymes are proteins, what is the monomer that makes them up? What's the monomer of it? Go ahead, Kathy.
Amino acids.
Good. So yes, enzymes are proteins, which means that they are made up of amino acids. Excellent. All right. So some new information that we're introducing today. Again, enzymes are catalysts, which means that they speed processes, they speed reactions up. The way that they do this is by affecting something called activation energy. Activation energy is basically exactly what it sounds like. It's a specific type of energy that is needed to activate or to begin a reaction. the amount of energy that is needed for a reaction to begin. If a reaction does not have that basic amount of energy, if it doesn't have the necessary amount of activation energy, the reaction can't take place. So I've always thought about this as a hill, and you all will see why in a couple of seconds. But in order for my reaction to take place, I first need to get to the top of the hill, kind of like a roller coaster. I need to get to the top of that hill, and then from that point forward, gravity does its thing, and I start rolling down the hill, and the reaction takes place. If I can't get to the top, then nothing happens. I'm just kind of going to roll right back down to my reactants. All right. So here, let's take a look. In this case, and in all cases, we've got a graph. This graph has potential energy on the y-axis, and it has time on the horizontal x-axis. So what this is saying is that as time goes on, we'll be moving from left to right on this graph. If we start off with reactants on the left side, here's a graph that depicts a reaction without an enzyme. So we can see we start off with reactants. They have to get up this hill. And then once they're at the top of the hill, they're just going to roll down and they will become products eventually. So a reaction is taking place here. And this reaction is not benefiting from the use of an enzyme. Here's a reaction, similar reaction, but with the help of an enzyme. Same reactants, they're becoming the same products, but we should notice something here. The hill is much shorter. So without an enzyme, the activation energy is represented by this red arrow. With an enzyme, the activation energy is represented by the green arrow. We can see that the green arrow is much shorter. So the benefit of an enzyme is that you lower the hill. It doesn't take as much energy now to get to the top of the hill, and so your reaction can happen faster. You don't need to build up as much potential energy. So the green hill, which depicts a reaction with an enzyme, is lower than the red hill, which depicts a reaction without an enzyme. And this means that it is easier and faster to climb. So I'm leaving this up in case you all are drawing this graph, but definitely make sure you have written down what's highlighted in yellow. Enzymes speed up reactions by lowering activation energy. All right. Excuse me. Sorry about that. I needed a swig of water. But looking at this picture, looking at these graphs, can we tell which reaction is using an enzyme? Is it the dashed line or the solid line? You all can send your answers to the chat. Which of these reactions is using an enzyme, the dashed line or the solid line? Okay, we've got Kathy saying that the dashed line represents the enzyme reaction, the enzymatic reaction. Anybody else want to pitch in an answer here? Does anyone agree or disagree with Kathy? And I see we've got a couple new people who've joined since I took attendance. So if you know that you showed up late, please send a message to the chat just saying that you're here. That will make it a lot easier for me to do my attendance. But Kathy, can you explain why you think it's the dashed line that's using an enzyme, or it represents an enzyme?
Because the hill is lower.
Because the hill is lower. Excellent. So that's how we can tell. It is indeed the dashed line. We can see that the hill is lower. It also says activation energy with a catalyst. Catalyst in this case is a synonym of the word enzyme. So the hill that's lower is always going to represent the reaction that is using an enzyme. We can see this hill is much, much taller. It's going to take longer to get over it. It requires more energy to get over. And again, we're moving from reactants to products. Another word for reactants is, of course, substrates. So we're moving from substrates to products. We've got to climb the hill first. And again, it's much shorter with an enzyme. So excellent job. And another thing to remember, we talked about this last week as well. Reactions can happen without enzymes. Even in the human body, there are reactions that can happen without the help of enzymes. But more often than not, we are using enzymes because why wouldn't you? It speeds things up and it requires less energy. So we can use these images to kind of depict that difference. The two people on the left are struggling to start a fire. They're trying to use a flint and a knife to do it, and it's just not working for them. That's like a reaction without an enzyme. Eventually, they'll get it. You know, it's going to take a lot of time. They will, work their fingers to the bone trying to start this fire. But the individual on the right is able to start it very quickly, as we can see. That's like with an enzyme. The reaction is going to happen rapidly. All right. The other thing that we talked about, enzymes are reusable. So an enzyme is going to go through a reaction. It might break something down, meaning it's going to do what's called digesting it, or it will synthesize something new, and then it's going to go right back into the same reaction and do it again. It's going to find something else to break down and then synthesize something new. So it's reusable. That's because ideally an enzyme is not going to change its shape. All right, so we want to think about some potential test questions. Last week we introduced those 4 biological compounds, otherwise known as biomolecules, otherwise known as macromolecules, otherwise known as polymers. Based on the diagram below, starch must be which of those 4 biological molecules? So here we've got starch represented with this red chain of hexagons. We can see that once the starch is broken down, it becomes maltose. So starch is being broken down by maltose. Which type of biological molecule is that?
Carb.
And how do you know that, Kathy?
because it's one of the examples, I think.
Okay, good. So we did talk about the fact that starch is an example of a carb. So, Kathy, I can tell you're obviously using your notes, which is excellent. Everyone should have access to their notes and should be referring back to them as we go through each day's lesson. But another way to know is that when we break starch down, it becomes maltose. Maltose ends in OSE. And OSE is the ending that always should signal to us that we're talking about a sugar. We're talking about a carbohydrate. All right, so Kathy remembered simply that starch is an example of a carb. That was kind of like the easiest way to do it and probably the best. So I definitely congratulate Kathy for using her notes, and everyone should be doing that. But the other way is that you might have noticed that maltose ends in OSE, and most things that end in OSE are carbohydrates. Sorry. All right. So two other words here that are important. You'll hear me use them sometimes throughout the course, not too often. Synthesis, as we can see in this image, represents building something new. So taking a couple of different things that are separate and distinct and combining them to build something new. That's what synthesis is. So enzymes can synthesize new molecules. They can build new molecules. On the other hand, they can also digest larger molecules into their separate parts. And to digest something means to break it down. So different enzymes do different things. Some enzymes synthesize and some enzymes digest. Okay, another practice problem. As it says, specific enzymes are used for specific compounds. When a compound is broken down from its polymer form, it gets broken down into its monomer form. So for example, in this first one, an enzyme called protease breaks down proteins into what? What is the amino? I'm sorry, I said it. I just said it. Amino acids, right? Because amino acids are the monomers of proteins. So protease is an enzyme that breaks down proteins into amino acids. It breaks them down into their monomer. Amylase breaks down carbohydrates into what? What should be in this blank? If I'm breaking down a carbohydrate, what should it turn into? If I break down a carbohydrate, what should it become? What's the monomer of a carbohydrate? Remember, we definitely should have that chart from last week's class written somewhere in our notes.
Monosaccharide?
Good. Thank you, Kathy. And I'd love to hear from some other people. Kathy, you're doing an amazing job kind of carrying the entire class right now. But I'd love to get some input from some other people, some other students. So amylase breaks down carbs into monosaccharides because carbohydrates are the polymer, monosaccharides are the monomers. All right, number 3, deoxyribonuclease breaks down nucleic acids into what? What should be in this blank? If I break down a nucleic acid, what's the monomer that I end up with? Where is everybody? We should be moving through these questions really quickly. We went over this several times last week.
Nucleotides?
Thank you, nucleotides. And the last one, lipase, breaks down lipids into, I'm just going to say it because I don't want to continue taking too much time. Glycerol and 3 fatty acids. So if you're like, I have no idea where this information came from, you need to be reaching out to me to schedule some time to meet, to talk. It won't take long, 5-10 minutes, or you can watch the previous week's lessons, or you can make sure you're doing your asynchronous assignments, which kind of explains all of this as well. But if you don't know these answers, that is a problem at this point, and we need to address that problem before it becomes too late, or before we start introducing more and more new material. So if you're confused, there's nothing wrong with being confused. There's nothing wrong with not knowing. The problem is that we've got to not know only temporarily. We don't want to not know forever, and we can address that easily and quickly. But I need to hear from you all. So Kathy, excellent job. Everyone else, let's make sure we're making our voices heard and getting the help that we need. All right, so at the bottom of the screen, we can see that the question is asked, what do all of these enzymes end in? So you can tell just by looking at these words: protease, amylase, deoxyribonuclease, lipase, that enzymes end in 3 letters, A-S-E. So don't be confused. Enzymes are proteins. We talked about the fact that carbohydrates end in the 3 letters O-S-E. But enzymes, which are proteins, typically end in the letters A-S-E. Okay, so that's another hint, another mental cue that you should be giving yourself. When I see those 3 letters, A-S-E, I should be thinking about an enzyme. When I see those 3 letters, O-S-E, I should be thinking about a carbohydrate. All right. So enzyme function. Enzyme function. Enzymes are very sensitive. Some of you might have some younger siblings at home who can only fall asleep under certain conditions. They need to be tucked in. It needs to be a specific time. They need to have a glass of water next to them. They need to have brushed their teeth right before. They need to be wearing a certain set of pajamas. They need to have a stuffed animal laying next to them or an actual animal laying next to them. They need to have used the bathroom before. So they will only go to sleep under these certain conditions. And if you can't meet those conditions, then here come the tears, here comes the tantrum. They need the night light turned on, whatever it is. So they have very sensitive desires and preferences for how they choose to fall asleep. Enzymes are similar. Enzymes will only function, meaning they will only work correctly in a specific environment. If even small parts of that environment are thrown off, it's going to be harder for the enzyme to function. It might still work, it might still do its job, but it won't do the job as well. And if you throw off too many conditions in that environment, then the enzyme won't do its job at all. So in the case when an enzyme is placed in an unfavorable environment, it will become denatured. And we're going to we'll define that word on the next slide. But again, I want us to think about that unfavorable environment. You might even draw the analogy to being in school. Again, if you're joining late, please send a message to the chat so that I can change my attendance. It's hard for me to go in and try to figure out who's coming in and who's going out. So if you're coming in late, please send a message to the chat. Thank you. Think about being in school. You all know which classrooms you like being in and which classrooms you don't like being in. You like the classroom where the teacher has Christmas lights hanging because the lighting is softer. It's not as harsh as those overhead lights. Thank you, Michaela. You like classrooms where the teachers might have an oil diffuser because it smells better in those rooms. You like classrooms where the desks are more spaced out because you don't feel as bunched up with your classmates. You like classrooms where the teacher allows you to get up and move around and stretch if you need to, but maybe not too much because you don't want to be distracted. But on the other hand, there are classrooms that you know you don't like. The teacher is going to lock you out as soon as that bell rings. The overhead lights are harsh and it makes it difficult to focus. Somebody always comes in smelling bad. The teacher never has any snacks or candy and is never going to let you leave to go get some snacks or candy. So in those environments, it's difficult for you to learn because it's an unfavorable environment. You don't feel comfortable. You might not feel safe. You don't feel like you have any friends or people who can support you in the classroom. So all of those things conspire to make it more difficult for you to learn. Enzymes work similarly. Again, when the conditions are off, it's not easy for them to learn. Or I'm sorry, it's not easy for them to function. Because I try to change my attendance and talk at the same time. So we don't want to throw the conditions off too much. Yes, Jason. All right. Mr. Moore's here as well. Alexander Moore, again, I noticed that you're here, but when you know that you're late, please send a message to the chat just so I can change my attendance and make sure it reflects your presence. Okay. So when an enzyme is placed in an unfavorable environment where it doesn't like to work, it becomes what is called denatured. And to denature is to change the shape of an enzyme's active site, which prevents the enzyme from working. To change the shape of an enzyme's active site, which prevents the enzyme from working. So we talked about the active site on Friday when we first introduced enzymes, but the active site is where the action happens. It's that open mouth of the Pac-Man, or it's that open piece of the puzzle. The active site is where the substrate is going to move in and where the chemical reaction actually takes place. So if I damage that active site, meaning if I change its shape, then even though that substrate might be there to move in, the reaction can't take place because the shape is now different. The enzyme and the substrate no longer fit together. This process of denaturization takes place when the environment is not ideal. This might happen because the pH is too low, meaning it's too acidic, or if the pH is too high, meaning it's too basic. This might happen when the temperature is too low, or the temperature is too high. So yet another analogy, I've thrown out a few. You can choose the one that you like and that makes sense to you. Another analogy is the bears and their porridge, right? One bear said that the porridge was too hot. The other bear said that the porridge was too cold. The other bear said that the porridge was just right. Enzymes need that porridge to be just right. They need an environment. They need to be surrounded by typically water that is the right temperature, the right pH. And those are the two things that we really focus on in this biology class. There are some other conditions as well, but for the most part, we're just thinking about pH and temperature. Every enzyme has a favorite set of conditions, and that favorite set of conditions is called the optimum. This is the most favorable environment where the enzyme works best. Okay. So again, we want to focus in this class specifically on pH and temperature as being the two conditions that we want to regulate for enzyme function. And again, central theme in this course of biology, shape determines function. If the shape changes, then the function changes. When an enzyme is denatured, that means its shape has changed. So that ultimately is going to change its function. All right. So graphing, we won't do anything too in-depth with graphing, especially in this virtual environment. But graphing is obviously an important part of science, and we often represent data by using graphs. So you all do need to know some basic information about graphs. Which color here represents the x-axis? Send your answer to the chat. Which color represents the x-axis here? Thank you, Jason. Yellow is the x-axis. So yellow is the horizontal line, and it represents the x-axis. Of course, that means that purple is the y-axis. All right, so that's very, very basic graphing information. Now, when we look at most graphs in science, they will have information on these axes. So here, the information that's on your y-axis is the rate of reaction. And the information that's on your x-axis is your pH. This graph depicts two different enzymes and how they function. Both of these enzymes can be found in the human body. This enzyme called pepsin is a stomach enzyme that helps us to break down carbs in the stomach. And there's another enzyme called trypsin, which can be found in the human intestines to help break down lipids. We can see that these enzymes are different based on how they're graphed. What's different about these enzymes? What is the difference between these enzymes based on how they're graphed? Again, what's the difference between these enzymes based on how they're graphed? Okay, maybe we don't know, but we can see pepsin, which is the black curve here, clearly functions at lower pHs than trypsin does, which is the red curve. Pepsin is functioning between the pH of 1 and about 3.5. Trypsin is functioning between a pH of about 5.5 and 10. Now, the most important thing to pick out from these two graphs is really this blue arrow. The blue arrow is drawn from the highest point in the graph down to the x-axis. And that tells you that the optimal pH for each of these enzymes is going to be found where the curve is the highest. So again, we can see that this curve is kind of going up. It's going to go all the way up. It will hit its high point, and then it's going to fall back down. This high point is called the optimal pH. Sometimes this will also be temperature on the x-axis as well. You just have to be able to pick it out. But the optimal pH here is looking like it's about 1.9. It's almost 2. For trypsin, the optimal pH is almost exactly 8. All right, so you want to find the high point on the graph and then figure out what the pH, or in some cases, what the temperature is to give you that high point. All right, so let's do some examples, some practice. Again, when the graph peaks, the enzyme is in its optimal environment. So what's the optimum pH here? What's the optimum pH for whatever this enzyme is?
8.
8, yeah. So we can see that the graph peaks at about a pH of 8. Now, the other thing we talked about, of course, is denatured enzymes. A denatured enzyme is no longer working. If these graphs are representing how well the enzyme is working, meaning the higher we are on the graph, the better the enzyme is working, then when the graph is at 0, when the curve is at 0, that means that the enzyme isn't working at all. That means that it's denatured. So at what pH is the enzyme denatured? What pHs?
11.
Okay, so close to 11. It looks like about 10 and a half. But is that the only place where it's denatured? I think I see another place as well. Where
Between 4 and 5.
good. So what we should say is that anything below about 4.5 or about 4.75, depending on how specific you want to be, anything below that, the enzyme is not going to work. So even though it doesn't show this on the graph, if we had a pH of 3 somewhere over here, of course, the curve is not going to be visible. The enzyme's not working. If we went even further to the left and we had a pH of 2 somewhere over here, again, that enzyme is not working over there. So anything below 4.75, the enzyme will be denatured. But there's another place on the graph as well that Kathy also pointed out. We're looking at about 10 and a half here. Anything above that, the enzyme is going to be denatured. So if we were at 11, enzyme's not going to work there. If we were to go further and have 12, the enzyme wouldn't work there. So anything above 10 and a half represents a denatured enzyme. Oops. All right. So I kind of gave the answer there already, but in this case, we're not looking at pH, we're looking at temperature. So the optimum temperature for this enzyme is 40. The graph is at its highest point at 40 degrees Celsius. At what temperature does the enzyme denature here? At what temperature does the enzyme denature? Jason says 50. But let's take a look at that. So if we were at 50, I'm just going to go up until I hit the red curve. It is as straight a line as possible. If I keep going up, I can still hit the red curve. The enzyme is not working as well here as it would at 40 degrees Celsius. But at 50 degrees Celsius, it is still working. So it's not denatured totally. Denatured again means when the curve has hit 0. The curve is you can't see the curve on the graph. So when does that happen here? When does the graph hit 0 here? 60 is better. I think we could be even better. We could say 62 or 63. But yes, when this curve is hitting 0, meaning when it hits the x-axis, I guess is how I should say it. When it hits 0 on the y-axis, meaning when it collides with the x-axis, that's when it is denatured. So anything above a temperature of about 62 degrees Celsius, the enzyme is not going to work. It's going to be denatured. All right, one more question, and I'll let you guys do your asynchronous assignment. So we've got a diagram here. The diagram labels several parts. We've got structure X right here, structure Y just below that, and structure Z on the far right. So the question is, which of the following is represented by structure X? Is it A, the substrate? Is structure X B, the product? Is structure X C, the enzyme? Or is it D, the complex? Which of the following? Kathy's got an answer. She says A. Anybody else have an answer? We're thinking about which structure X is here. And this is very, very similar to number one, something I asked you all to draw in your notes last week, and number two, something that will appear on your test on Thursday. Any other thoughts as to what structure X is? I've only got one answer in the chat. I think we can do better. There are 18 people on the call. Okay, Kathy, you are right. Thank you again. All right, so we'll find some ways to make this a bit more interactive because I need to know if you guys are understanding this stuff and if you need help. There's nothing wrong with needing help. There's nothing wrong with being wrong. The problem is when you choose to remain in that state of wrongness. So if you need help, we need to address that and move past it. And that requires me to hear from you all, besides just Kathy. Okay, so Kathy, you're doing a great job. It appears that you don't need help right now. Today, we've got a couple things to do. We've got an exit ticket. And then I also introduced this assignment on Friday as well, but I am giving you guys, of course, the option to continue to do it today. It is U1D5, Amoeba Sisters Enzyme Video and Quiz. Some of you I know have already done it. And if that is you, then all you need to do is the exit ticket and make sure you've stayed up to date with your other assignments. Ignore this. You guys are not in my honors class, so this does not apply to you. But we've got two things that we need to make sure we've done today. And of course, stay on the call and keep studying. And if you have any questions, you can ask. So we've got the exit ticket and we've got one assignment. I will leave this screen up. I'll put myself on mute if you all have any questions. Other than that, everybody knows what they should be doing and you should get to work. Okay, folks, I'm sorry I lost track of time. We're 2 minutes after 11:35, so you all should go ahead and enjoy your lunch break before fourth block. I appreciate you all being here today. I want more participation tomorrow. We can always be better tomorrow than we were today. But enjoy the rest of your Tuesday, and I'll talk to you all on Wednesday.